In the last video, we looked at how to calculate the maximum entropy of a probability distribution. In this video, we're going to actually calculate it in Python, and we're going to see how the central limit theorem still stands when the entropy is maximum. So let's take a look at how we're going to do this. So first of all, what we want to do is write a function that actually calculates the maximum entropy. So that would be, we define a function, let's call it negative entropy. Negative entropy, which takes probability as an input. We already calculated in the last video that the negative entropy is going to be equal to P times, actually it's going to be the NP nullPy.sum of all the probabilities times the natural log of the probabilities. So that's our negative entropy. We calculate that, and from here, what we want to do is we want to minimize this function, because remember, the maximum entropy is actually negative of this particular function, so maximizing it would mean minimizing the positive value. So that's what we're going to do. So in order to minimize a function, we need to first import this particular module, the minimize function from the SciPy optimize module. I've already done that here, as you can see. So we're going to use the minimize function, and the parameter it takes is, first of all, it takes the function. So our function would be equal to negative entropy, and after that it takes the initial guess, which is denoted by x0. I'm just going to call it p0 for now. We haven't started the variable yet, but we will soon. We basically have to give the initial guess of the independent variable for the function, which is the probability. On top of this, what it also needs are bounds. We'll talk about this soon as well. So first of all, there's a bunch of things that we clearly need in order to minimize this function. So first of all, let's say that our sample size has 101 samples, and then let's say our grades equals np.arrange, and what I'm doing here is basically this grades variable will store all the different possible groups in which our 101 values can be arranged. So there's that, and then our p0 should be np.full. This np.full basically takes two arguments: the size of the array and the number with which the elements will which will be used to fill in all those spaces. So I'll start with n comma this is 0.01. Before we go anywhere with, actually let's just do this as well. So my bounds are basically the limits within which my values will be at. So that's basically 0 to 1. So I will send the value of from 0 to 1, and I'll multiply this by n because I need that many unique values between 0 and 1. So there's that. We also need various constraints, but we will talk about that later. But before we do any of those things, let me show you what these various variables look like. So our grades variable are going to look like this. So it's basically a function with 101 elements from 0 to 100. Likewise, our p0, our initial guess for the probability, is basically an array with 101 elements, all filled up with 0.01, which will be the probability. This isn't exactly accurate, but it's just an initial guess, so it doesn't really matter that much right now. So we have that. Alright, so let's take a look at what our minimize function looks like. So it gives us this huge answer, and basically this minimizes all the values, all the probabilities. And it gives us this particular array. This is the one that we're looking for. So I'm going to store this in a function, say pdist. So our probability distribution equals, I'll just I'll just store this thing under a variable called pdist, or probability distribution. So let's do that. And so we've got that variable stored. So once we have that, what we want to do is obviously to plot a graph. So let's say fig equals make underscore subplots, brackets, and then fig. We want to add a bar graph. So there's that. Here our x-axis should be the values of our grades, and our y-value should be all the x inside of the probability distribution function. So that's y would be equal to p distribution dot x. And finally, a few touch-ups. Let's update the layout of the graph. Underscore layout. I want the width to be 600, the height to also be 600, and there's a mistake there, let's turn that to a comma. And finally, we also need the template to be plot the dot. So let's see what it looks like. Okay. For now, it just looks like a bunch of bars, which is fine because we haven't given any constraint to the minimization function. All we've given it is the bounds within which our variable should be at. So let's start by adding some constraints. So the first constraint that we can think of is that the probability should not be over 1. It should be between 0 and 1. So let's add that constraint right away. So constraints should be written as functions such that it returns a value of 0. So solving that function should return a value of 0. So one way to write that would be let's define a function. Our first constraint C1 takes the probability as inputs and returns np.sum of probabilities minus 1 should be equal to 0. So that's our first constraint. So let's add that constraint to our distribution function as well. So I'll add that as constraint. Constraints. There's a unique way to write the syntaxes for constraint. So it starts with a list within which we give a tuple, and inside that we first give the type as EQ, which means it's equality. And then our function is passed as function colon our function VC1. So let's run that and run the graph again. Yeah, so we did this, but nothing really changed except that the probabilities have been, the sum of the probabilities should be 1 now, whereas it might not have been the case earlier on in the last graph. So according to our question, let me see where I put the question at. Okay, there we go. So according to our question, we want to demonstrate that the given average and standard deviation have to be used as well. So let's do that as well. So let's add another constraint for the mean. So, and before we do that, let's take a look at how we're going to create those functions. So we know that in order to make what we already know is that the mean, or x bar, is actually equal to sum of all the values, xi, times their frequencies divided by n. Now, what we can also say is that the probability of a value I is actually equal to its frequency, so add an I here too, divided by the total sample space. So what we can write the frequency as is, so we can write frequency as pi multiplied by n. So let's do that. So that would be summation xi times pi times n divided by n. So since this n is actually a constant, it can come outside of the summation sign and can be cancelled with the denominator. And what we end up with is basically summation xi pi. What I'm also going to assume here is that our mean, with 101 values, our mean lies somewhere in the middle. So let's say 50. So 50. So therefore our function will be summation xi pi minus 50 equals 0. So let's write that down as a function. So what we do now is define C2 as our second constraint, taking probability as the input, and we return np.sum of the probability times the grades. So xi is basically all of the actual values, so that would be grades. And we subtract 50 from it so that the right-hand side is equal to 0. So let's add that constraint in as well. So basically what I'm going to do is copy this constraint, add a comma there, and paste it, and write that as C2. Let's see what change that makes. C2, okay, I need to run this first. There we go, and yeah, no change whatsoever. Basically, our mean was already 50, so nothing changed in this case. So now we need to add our final constraint, which is the standard deviation. Now, what we know about standard deviation is that, let me scroll down a little bit. What we know about standard deviation is that the standard deviation is equal to the square root of the summation of the individual values minus the mean squared, that's a 2, not a 3, squared, okay, let's try that again, squared divided by the total sample space. Now what we can do here is, let's do that. Okay, so let's do that, and what we can write this as is that it's the summation of n times the probability of I times the individual values minus the mean squared divided by n. Again, this is a constant, so it can come outside of the summation and it can be cancelled by the denominator. So what we end up with is the square root of summation of the probability of I times the individual values minus the mean squared and square root of the whole thing. So again, let's write that down as a function in Python. Okay, so the new function C3 constraint 3 takes P as input and then return np.square root of np.sum of the probabilities times the individual values, which are the grades, minus the mean squared. So we need to also start our define our mean. It's going to be x is equal to, which you've already done here, so I'm just going to copy paste. Again, we want this function to return a 0, so I'm going to subtract, say, 15 out of this. So let's run that again. The whole thing. So we actually also need to input that constraint here as well. So let's make a copy of that, comma, paste, that's C3. Let's run that again. It shows us an error, but that doesn't really affect our calculation, so I'm just going to go ahead with it. So yeah, even with the maximum entropy, we actually get a normal distribution by using the central limit theorem.